Alright, so the last thing we talked about in class was our VSEPR models. And remember, we're talking about the valence shell electron pairs and their repulsion overall. Okay, so when we are talking about the overall shape, the shapes are going to change based off of how far apart those electrons want to be. And so we talked about how there are 6 domains or 6 areas around the central atom, and then from there, depending on how many bonds and lone pairs there are, will determine their molecular geometry. And so refer back to your notes and to your cheat sheet for further detail about that. So when we are considering drawing any molecule, we have to first consider its Lewis structure. Okay, so when we are looking at methane, when you guys draw your Lewis structure, it's going to look like this. It's going to be kind of a stick figure, and this is our 2D model that we have been drawing for about a week and a half, 2 weeks now. Okay, although that your model looks like this, with the VSEPR model, we know that these electrons are not as far apart as they could be, because we're not just looking at one plane when we are talking about shapes. We're looking at all different planes, all the possible areas around a central atom, which is a full 3D model or a full 360 sphere circumference. We're looking at where those electrons could be and how far they could be spread apart. So when we look at the VSEPR model, or a more accurate 3D model, we actually see that CH4 looks like this. Okay, so you guys usually look at it from the side like this, and that's where we get our 2D model. However, if we look at it from the bottom, we would see only 3 prongs. If we looked at the top, we can kind of see all 4, with the top bond or the top atom and the central atom lining up. So when we are actually looking at a compound, we need to consider its 3D VSEPR model and how those electrons are as far apart as possible. We cannot consider it like this because they're not as far apart as possible. If we look at these hydrogen bonds, this is only 90 degrees apart. But if you look at your cheat sheet, we know that a tetrahedral, or anything with 4 different domains, is going to have a 109.5 degree difference. So then that way they are as far apart as possible because they are all negative charges and repelling each other. That in mind, when we talk about polarity, we are considering what happens when there is an uneven pull on electrons. Okay, and so when we're looking at an uneven pull on electrons, we kind of think tug of war. Okay, so if I have one person right here who's super strong, and I have one person over here who's only slightly strong, I do apologize for the focus. Okay, when I have somebody who's super strong over here and someone who is slightly strong right here, we know that when they are playing tug of war and there is a flag right here in the center, okay, or 2 flags in the center depending on the tug of war you're playing with, the super strong person should have those flags near them more than this person over here, and that's because this person has a greater pull. So that's like if we were looking at hydrochloric acid. So say hydrochloric acid was drawn like this. Okay, chlorine has a stronger pull on electrons. It wants those electrons more to have a complete octet than hydrogen does, and so that means that those electrons are going to spend more time with chlorine than they are going to spend with hydrogen. This is polarity. This shows that this object is considered polar because there is an uneven pull on it. Now, the way that we know that there is an uneven pull on it is based off of our electronegativity. Right? And so when we are considering electronegative objects, we look at the electronegativity chart. Alright, looking at this electronegativity chart, remember, electronegativity is the ability for an atom to attract electrons. And we know that electronegativity increases to the right and it increases as we move up. And we can see this because down here in the bottom left is the smallest number, 0.7, for its electronegativity. And then we have fluorine all the way up here in the top right corner, that's 3.98 as its electronegativity. So going back to our tug of war example, if I was looking at hydrochloric acid, and I'm going to pull this over here so you guys can see it better, I could consider its electronegativity if we had the values chart in front of us. Okay, so I see that chlorine has a value of 3.16 and hydrogen has a 2.20 value. Okay. So when I'm considering the electronegativities, what I do is I find the difference between the two, or I subtract the two numbers, and that gives me its electronegativity or its electron attraction difference. Okay? So when I'm looking at this, I get about a 0.96 difference. Okay? Because of this difference, I can use another set chart or set organizer that tells me if something is ionic, covalent, or polar covalent, covalent, or nonpolar covalent. So I look at my difference, which was 0.96, and I see that it falls right here in this range. So that tells me that the object I'm looking at is polar covalent, or the molecule I'm looking at is polar covalent. Well, we just talked about how this tug of war between the two is considered a polar object or a polar molecule, and we know this is covalent because we have two nonmetals. Okay, so if we had the values all the time, we would be able to see that this is a polar object because of the different values that are given. If we are given the chart, it makes it super easy because then you can just subtract the two numbers and compare it to your bond type chart at the bottom of the page that I just showed you, right here. But what happens if we do not have this chart? Well, if we did not have these numbers on this periodic table, we just use what we know about electronegativity, which brings us back to periodic trends. As we move further to the right and further up the periodic table, we know that it becomes more electronegative or more ready to pull an electron. So when I'm considering those values, that helps me determine the overall polarity. So, thinking about tug of war, okay, I can take an object like BH3, and I can put boron as my center, and I would still draw my Lewis dot structure like normal. Okay, so I know boron has a total of 3 electrons plus 3 from hydrogen, placing 6, so 2, 4, 6. All right, so this is my correct Lewis structure. And so when we're thinking polarity, we think, does it have an even pull? That does not mean, is it a perfect line of symmetry? So if I halved it this way, would it be perfect? Because we can't think like that because of the Vesper model. When we are looking at a Vesper model, okay, they are not going to be sitting across from each other all the time. They are not going to be diagonal to each other all the time. However, if they are the same atoms around it, it's going to cause an even pull on each side. Say I have a person with the same strength as these two other people. That means these 3 people have the same strength. If they're playing tug of war, they're pulling all in different directions, but at the same strength, that there's going to be a standstill in the middle where nobody is pulling harder, where that flag is going to stay in the same place. So if it's staying in the same place, that means there is an even pull. And if there is an even pull, that means that the object is non-polar. Okay, so hopefully that clears up some of the polar and non-polar questions. Okay, the best way to look at this is if you look at the Vesper simulator that I posted on Google Classroom, you are able to look at the shapes and see if from every angle are all objects going to even each other out. So even if you think it's going to even out perfectly, there are situations like this where it's not even on all sides. Okay, you may think, oh, this is non-polar because there's an even pull on these two ends and these two ends. But remember, we are not thinking 2D, we are thinking 3D. So in this particular example, I have 2 hydrogens and 2 chlorines around a central carbon. So when you look at it, it would look kind of like this. Okay, in its Vesper model. You would think that it would be non-polar because it's even on these ends and even left to right. Well, that's not the case here, because if I just turned it to look at it maybe from this side, I would see that these are not always across from each other, or my chlorine values are not always across from each other, and my hydrogen's not always across from each other. If I looked at it this way, it's not considered an even or a symmetrical shape. And so that's why we always have to refer to the Vesper model or really consider what's going on. So usually if we're looking at tetrahedral, unless all sides have the same atom as their peripheral atoms, it's not going to be nonpolar. Instead, it's going to be considered a polar object. And so that applies to all shapes. If all peripheral atoms are the same, you're going to see an even pull in all directions, making it polar. And of course, there are a few exceptions that happen that we'll talk about more. When we are looking at an object that has a lone pair, so say we're looking at this, okay, and we would say that this has a lone pair right here, and then it has 3 atoms that are the same. The lone pairs are considered their own atom, their own pull. So even if these 3 people are pulling the same amount, maybe down and to the left, down and to the back, and down to the right, the person that's pulling upward has a higher strength or a different strength than these 3, so it still creates that uneven pull and would make it a polar molecule. So once you decide if an object is polar or nonpolar, you do look at the intermolecular forces. And you have to forgive me, I've been teaching this all day, so my mind is drawing a blank. But once you decide something's a covalent compound, so they are sharing electrons, you have to decide, is it polar or nonpolar? And we've already said that if it's polar, there is an uneven pull on electrons. And if it's nonpolar, there is an even pull. So with this in mind, we have to see how molecules are going to interact with each other. So if I looked at my polar molecule of water, we're not looking at intramolecular forces, so what's happening between this oxygen and hydrogen. We're looking at what happens if we added another molecule and how these 2 different molecules are going to interact right here. Okay, so when something is polar, it's considered to have a partial negative charge and a partial positive charge. Okay, and we represent this by a lowercase delta sign. And so whichever one has the highest pull is going to get that partial negative charge, whereas the other one's going to get the partial positive charge. So when we compare 2 molecules together, the negative and the positive are going to attract each other. And from there we can decide, is this a hydrogen, a dipole-dipole attraction, or a London dispersion attraction? Okay. And so when I'm looking at polar objects, because it has a positive and negative charge that pull together, it's usually a somewhat strong intermolecular attraction. So it can be hydrogen, or it could be dipole-dipole. For it to be dipole-dipole, the interaction has to not be one of these 3, an H and F, H and O, H and N. So only hydrogen bonds can form when hydrogen and fluorine, hydrogen and oxygen, and hydrogen and nitrogen are interacting. So here in this example with water, I see hydrogen and oxygen are interacting. So it's going to have the strongest intermolecular force of a hydrogen bond. Whereas anything else, like say we were looking at hydrochloric acid, when it interacts with itself, it's going to be dipole-dipole. So this is pretty much any other polar covalent compound that does not have these different combinations. So when I look at hydrochloric acid, I have to decide if it's polar or non-polar first, and I know that chlorine is far on the right side of the periodic table, which means it probably is going to have a higher electronegativity, or it will have a higher electronegativity based off of the periodic trends we've talked about. So that means if there's a higher pull, the dipole moment, or the moment where the electrons spend the most time, is going to be with chlorine. So that gives it a partial negative charge, giving hydrogen a partial negative charge, or partial positive charge, excuse me. So when they interact together, positive and negative are going to interact together. And so this is my intermolecular force. And because it's not hydrogen and fluorine or oxygen and nitrogen, this is automatically a dipole-dipole intermolecular force. So when you are looking at objects like CH4, or molecules like CH4, we can see that there is a sense of symmetry. And I've already told you, if there are the same peripheral atoms around any central atom, it's going to be nonpolar. And we can see that if we turn this in any direction in its 3D model, that it's going to have a symmetry to it, or the same pull on all sides, making it nonpolar. And all nonpolar objects are considered to have the highest intermolecular force of London dispersion. And that's because there is no positive or partial negative charge on these molecules. So when these molecules interact, okay, whether it's a little bit with this hydrogen or this hydrogen and this carbon together, it's not really a strong pull, and so these London dispersions basically kind of release the charge or disperse the charge a little bit and then pull it back in to where these are interacting, but there's not a strong pull like we see with a positive and negative, and that's what makes it nonpolar. So if we consider something to be nonpolar, that automatically gives it the highest intermolecular force of London dispersion. With all of this being said, we can use intermolecular forces to identify properties of different molecules. So just like when we are looking at water, water is considered polar, okay? And so we know water is considered a universal solvent, or it can dissolve a lot of stuff. And so when we are looking at polarity, we know that like dissolves like, which means polar dissolves polar, and nonpolar dissolves or dissociates nonpolar. And you learned this in your previous classes before, okay? We know that water can dissolve salt, and it can dissolve several other objects that are polar. We know salt is considered sodium chloride, and it is an ionic compound, okay? And it does have a large polarity, such a high polarity, in fact, that it rips those electrons from sodium and gives it to chlorine. So that's why water is capable of dissolving salt, because like dissolves like. Whereas we know oil and water can't mix, and that's because water is considered polar, and then our oil is one huge hydrocarbon chain, which is a bunch of repeating carbons and hydrogens. And so water cannot dissolve our oils because it's not the same polarity or the same pull on electrons. So what happens is polar can't dissolve nonpolar. Instead, we would have to get something nonpolar to dissolve oil. So if we look at petroleum, petroleum is considered a nonpolar molecule, so it could dissolve oil, okay? So this is a brief overview of polarity. I'm going to post some other videos. My suggestion is to really use that Vesper simulator to help you out and to really get your head wrapped around the fact that the shape is what determines its overall polarity based off of how electrons are pulling in several different directions. Okay, so if all of the atoms, peripheral atoms in the shape are the same, it's going to be nonpolar. If there's anything that's different, then it's most likely going to be polar with a few exceptions. And of course, tomorrow in class we'll talk about those exceptions, but this is the basis for our intermolecular forces and polarity.